All right, now we're going to finish up the 7.1 lecture on equilibrium. If you will remember, we left off with writing these equilibrium expressions, and you may or may not have practiced these, but it's really good to make sure that you get those correct, because that's going to kind of be the first step as we move forward and do some quantitative equilibrium where we actually calculate some of these guys. Right now we're kind of just talking about the concepts. And when you put together an equilibrium expression, you remember the gases and aqueous ions. You include those, and you do not include liquids and solids. That's something that I think should make a lot of sense to you. Okay, and now moving on, we're going to talk about something called the reaction quotient. It describes the relative concentrations at any given moment. Okay, so a system, an equilibrium system, doesn't have to be at equilibrium at a given moment. If Q is equal to K, then yes, then it's at equilibrium. But I think this is best described, and just bear with me, I'm going to go back quite a few slides here. When you talk about concentrations of these things, and we could change the concentration of either one of these so that they could go up or down, and it would take them a while to bounce back to equilibrium. So when you're at times like this, and looking at the rate, during this time, this would be a Q situation. Okay, the rates are not equal at that time. Here you would have the forward rate being greater than the reverse rate. So maybe, for instance, somebody dumped a bunch of N2O4 into this system. That would increase that concentration a lot, and it would mean that it wouldn't be at equilibrium. So the system then would change and eventually reach equilibrium. But at any given moment in time, Q, it does not have to be at equilibrium. So that's what the key change to what we're doing. Now, you will notice if you look at how you write a reaction quotient expression, it's the same thing. Products over reactants, the coefficients become exponents, and it's the same rule. And if it's QC, that means concentration, and concentration means brackets, which of course is moles per liter. All right? So if you were going to write the reaction quotient, QC, for this reaction, you could look at it, just do a quick overview, and you see, yep, nice equilibrium system, double arrow, solid. You're not going to worry about it, are you? Aqueous ion, we're going to worry about it. Solid, no sweat. And over here, another aqueous ion. So when you're writing the QC, you follow that same format, and so we just set it up. QC equals the products in brackets, raised to the third power, there it is, 3, over the reactants, in this case there's just one of them, raised to the second power, 2. Pretty straightforward stuff. But you do need to know the difference between K at equilibrium and Q anywhere. Could be equilibrium, could not be. Any type of concentrations on both sides. So usually Q is used to represent the situation where it is not at equilibrium. All right, now KP. We said that the general term is KEQ, and KC is concentration. KP, there's going to be a lot of P's here. I mean, think about it. It's partial pressure. And when you use partial pressure, you notice you don't use brackets. Partial pressure uses parentheses. So P, 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 all over the place. There's P all over. Whoops, that sounded weird. So K sub P, you got the parentheses right away. And realize that I'm going to talk about the partial pressures of these gases. Now, you always write the P. If you're going to talk about the partial pressure of a gas, you write P sub, if it's neon, Ne. If it's oxygen, P sub O2. If it's propane, it would be P sub C3H8. And you put the formula of the gas. So that's why these letters are written as subscripts. And people wonder why I hassle about typing up chemistry stuff. If you look at this, here you have a fraction, and on the top half of the fraction there is a subscript and a superscript. How do you do that all in one thing? You just can't. It's impossible. Mr. Kashi tells me it's possible, but I always just use little text boxes and slide them in there. So anyway, I digress. So you're not going to be, it's not concentration, so you're not talking about grams per mole. You're talking about ATM, atmosphere, is what is usually done. So K sub P is the pressure equilibrium constant. And it only would apply for gases, partial pressures. And remember to use parentheses in that case. All right, and if you will remember when we talked about partial pressure a little bit, so you look at the pressure in this room right now, most of it's caused by nitrogen gas, but there's also a partial pressure of oxygen gas and CO2 and neon and all kinds of different gas molecules making up that pressure. Now, the very interesting thing about gases, and this is why at STP there's always 22.4 liters per mole, is 1 mole of any type of gas will exert the same pressure as 1 mole of a different type of gas. So you're like, how is that possible? Those little ones are moving faster. Right, they are moving faster. Ke equals 1/2 mv squared. Their Ke is equal because temperature is a measure of kinetic energy. So the little guys are moving really fast, and the big guys are rumbling, bumbling, and stumbling along nice and slow. So therefore, they exert the same pressure. If you were to take 2 moles of gas, that would exert twice the amount of pressure, as it says there. Okay? So, if we were going to write a Kp expression for this guy right here, you see, we're going to include everything. So you would write Kp parenthesis, so P subscript, and you write the formula of the gas. That is how you write it. Just, you don't, when we first introduced it, we talked about P1, P2, P3. Don't do that. Write the formula of the gas. All right? And again, don't put gas in there. The G, leave it out of there. That is a nice little equilibrium expression for a Kp using parentheses. Holy smokes, what the hell? Round brackets instead of parentheses? Is that a Canadian thing again? Round brackets. A bracket is square. Bracket. Wonder if their brackets for NCAA are rounded. They have some are round and some are square. Brackets are square. Don't ignore that. Pretend you never even heard that because parenthesis works for our thing. Kp parentheses. Okay, so don't use square brackets. Use parentheses. All right, so K sub P. So already we know two types of K values. Well, you might be asking, would that work for Q? Well, obviously, yeah. We talked about, you open the top of your Orange Crush. You can hear the equilibrium shifting, all right? So that would be a partial pressure example. And yes, the reaction quotient, QP, would describe the partial pressures the same way. And then when it was at equilibrium, KP would equal QP. So at any given time, you can change the amount of gases, you can change the pressure on the system, and it will take it a while to get back to equilibrium. So for a while, it's not at K, it's at Q. And especially if systems are being manipulated, changed a lot, then they will be in Q most of the time. But given long periods of time undisturbed, they achieve K and stay that way. All right, so write the expression for the reaction quotient QP for this reaction. Give it a try. Hit the pause. Try it. Pause. Hit the pause. Thanks. Okay. All right, let's see how you did. It's actually quite a simple answer. Boom. That's it. Nothing on the bottom, because that's a solid. And that's a solid, so you leave that out. So it's just these two with ones. So you're using these parentheses. I'm not going to say round brackets. Okay? Q, P, and you just multiply those two things together. So you now have the technology to finish all of the problems. They will be due after the long weekend, first thing in the morning, along with the other assignment we're going to give on Friday. Okay, so we'll do one more equilibrium lecture. Remember that this one is an assessment, so do a good job of answering the questions completely so you can get full point value on this assessment. No answer key, sorry. All right, super duper. This is day 2 of lecture 7.1. This is the third of 3 lectures. So you are now done with 7.1, and we're going to move on to the next lecture in the equilibrium packet. See ya. It's always that awkward time where you're like looking for the bye, and then you're like,